Good evening, everybody. My name is Sarah Hart, and I am the former Gresham Professor of Geometry, so I'm delighted to be able to introduce the current Gresham Professor of Geometry to speak this evening. Alain Goriely has given wonderful lectures this academic year on nature's shapes, and this is the next in that series. So we've had chirality, handedness in nature, we've had shells, we've had gravity and what effects it has on the shape of things like planets. And this evening we're going to hear about tiles. But before we start, I wanted to just do a little bit of housekeeping, just in case you haven't been here before. And even if you have, you may have noticed that you came in a different entrance from your usual one. There's some building work going on at the front, so we needed to send you around the other way. But you've all found your way here, so top marks already for geometry in real world. Just to mention, at the end, we'll have a few minutes' time for questions to the speaker. If you are watching online, you can ask a question by scanning the QR code, which will get you to Slido, which is our medium through which to ask questions. If you're in the room, you can either raise your hand in the time-honoured way, or there are QR codes which you can scan on the screens at the side here, so that can be your choice. I will have a little tablet here which I can look at the questions and then ask Alain to answer them. So that'll be happening at the end. One other little thing is that I wanted to sort of advertise to you that Alain has, in the last year, been awarded a prestigious medal, the David Crichton Award, which is jointly given by the London Mathematical Society and the Institute of Mathematics and its applications. And the award was made last year, but the lecture and medal presentation for that is soon to happen. So if you're free on May the 13th and want to go to the Royal Society in London to see Alain give another lecture, then that'll be an amazing occasion, and I suggest you go online and find out how to do that. But I think, this is really, really great achievement, and we're all very proud of him. So without further ado then, let me introduce Professor Alain Goriely to speak to us on the shape of tiles.
Thank you so much, Sarah, and thank you all for coming, and for people joining us online, thank you also for joining. So, as part of the series of the geometry of nature, today I will talk about wonderful topics, the mathematics of tilings. So, but before I start, I want to acknowledge my good friend Gabor Domokos from Budapest, who had been working on this type of problems for many years, and a few years ago he invited me to join in one of the projects, the one I'm going to talk about today. And this talk is mostly going to be based on two papers we co-author with Akos, who is professor of mathematics, same university, and Christina was a brilliant PhD student who has since graduated. And the work that I have here is mostly going to be based on this article from 2024, and the last part on that most recent one that was accepted only 2 weeks ago in the proceeding of the Royal Society. And also, I want to acknowledge that I'm very grateful to them because they've also shared some of the brilliant visuals that they've been developing and that I will be using for this talk. So, I'm going to talk about tiling, both in the plane and in space. And as usual, it's much easier to start talking about things in the plane. So let's start with planar 2D tiling. Here are some examples I'm not going to go through. You see there are mosaic, there are patterns that you find in nature, there are patterns that you find in technology. So what exactly is a tiling? Well, here is another example, a beautiful example that I love because it's from the Alhambra in Granada. It's from the 13th century. So a tiling is a covering of a plane or space by shapes, and we're going to call them tile or cells for these talks. And the condition is that these different cells have to fit together exactly with no gap and no overlap. And you see the tiles, the cells in this case, can be made of polygonal shape with straight edges or with curved ones. We're going to consider both, and that's going to be important. So let me give you a few more definitions. You can have what we call monohedral tiling, made of a single shape that covers the whole space. Things, for instance, square. But here is a better example. There is a delightful little book by Hokusai, the same Hokusai from The Great Wave. And in his book, he studies patterns and tries different types of patterns that do exactly what I told you, which are tiling made of single or multiple shape. In this case, we call it monohedral because the shape is polygonal shape. It's made of straight edges, straight faces, by opposition to monohedric tiling, which are tiles that are made with curve shape. And here is an example, a beautiful example recently discovered in 2024, which is called the Spectre. It's a monotile, so this single tile covers the whole plane without ever a periodic repetition of any pattern. It's an aperiodic tile. It's quite wonderful because people have been looking for that for the last at least 50 years. And I brought a few of them here. If you want to come after, I invite you to join and look at these in more details. This is tiling that's done with a single cell, but you can do with multiple cells. You can do a polyhedral tiling, polygonal in the plane, polyhedral in general. And here is Roger Penrose on the Penrose tiling. So back in 2020, when he received his Nobel Prize for Physics, we were in lockdown, and Daryl, who's sitting here, asked me, said, well, the Nobel Committee wants some picture. Can you take some picture of Roger? And so I went around, took some picture, they put it on the poster and all that. And the two of us were the only one in his acceptance talk that we had to film at the time. The Penrose tile is one of the things he's well known for. The Penrose tile here, the one in front of the Andrew Wiles Institute, Andrew Wiles building, the Mathematical Institute in Oxford. It's made of two rhombi shape that you can put together. And again, this is an aperiodic tiling that looks like that when you see it from the top. He added Roger design on top of that, some circle to make it nicer. Very, very interesting. You can have a polyhedric tiling, for instance, from Escher, where the shape tiles, different shape tiles the entire plane, but this time with curves. Okay, so here is another example from nature. This is cracks forming in lava that has not yet completely solidified. And we're going to take the ideal version of that, and the ideal version is a tiling, and you can imagine it goes on forever. And in this tiling, you have different entities. You have two different mathematical objects of importance. You have the cell, and you have the node. And what we want to do is assign numbers to that in order to quantify and compare different patterns that we observe everywhere in nature. Before we do that, there is an important distinction about the cell. A cell can be convex or non-convex, that's a technical term. It's convex if the line that I make by choosing any 2 points in the cell is also in the cell. So in this case, it's in the cell, and the one on the right is non-convex because there are points for which the line is not entirely within the cell. Okay, so it turns out that the mathematics of convex cell is much easier because it puts more constraint, and so that's a big difference when you try to establish general results. Okay, so what is a node exactly? A node is a place where you have at least two edges meeting. And now I look at the cell, and I look at its boundary, its perimeter, and I can count the number of nodes that are around the cell. So I can assign to the cell that number. In this case, there are 5 nodes around. But there is an important distinction here between the difference between a node and a corner. Because if you have a node like the number 5 here, where the edges meet a T shape, well, there are only 4 corners within the cell. So if I'm in the cell and I look around, I would only see 4 corners in this case, right? The shape would have 4 sides. And so I make a distinction between the number of nodes and the number of corners. It turns out we're going to mostly look at corners and trying to soften them in due time. Okay, so now we've assigned these numbers, these 2 numbers, on a cell. What can we say about the nodes? Nodes are always like dual from the cell. Well, you can look at one node and look how many cells there are around. Just like we look at a cell and how many nodes there are around, we look at a node and look how many cells there are around there. So for instance, in this node, there are exactly 5 cells around it. So we call it the degree of a node or the degree of a corner. In this case, there are only 4 corners meeting there. Right? So let's look back at our little example. Here is an example of a regular node. There are 3 edges meeting. And here is an example of an irregular one. you see that there are 3 cells meeting at that node, but only 2 corners, because one is flat. Okay, big difference. And for the cell, this cell has 5 sides. It's a pentagon, but there are 6 nodes around it. Okay, and I'll mostly be interested in the V star, not the V. You'll see why in a second. Okay, so now I can consider any type of tiling, and I want to assign a single one of these numbers to the whole tiling. So what do? I pick a point, I look in a circle or a ball of radius r, and I count I average these symbols for each one, the degree and the number of corners. Then I take the limit as r goes to infinity, and I obtain a single number for that. So that gives me 2 numbers, and there is an extra one, which is the proportion of regular nodes. So the total number of regular nodes divided by the total number of nodes for a radius, and I increase this radius and take the average again. So in this case, for instance, there are 11 regular nodes, all the red ones, and there are 4 irregular ones. So P is 11 divided by 15, and P is a number between 0 to 1. It's 1 when all the nodes are regular, there is no T, and it's 0 when every node has a T shape. So out of that, I get 3 numbers, V star, and P. Okay, let's look at a few examples so we get a little bit use of what that means. The simpler one, of course, the square lattice. If I look at a node, each cell has 4 sides, and 4 edges meet at each node. So I have 4 and 4. All nodes are regular, right? There is no T junction. And you find plenty of examples, and I can never resist giving example from Herbert Hooke, who was Gresham professor of geometry, whose name is on the side here of the room. And here is an example from Micrographia from 1665, very interesting book where it does the first microscopy book. It's also the first international scientific bestseller ever. And in there, it looks at tissue. And for instance, the cork is a very clear square lattice that he dissects and draws within there. It's also the book where the word cell is introduced, the same word that we later use in biology for a cell. Another example is the hexagonal lattice. And here you see that I have the shape a 6-edge hexagon. So V star equals 6 for each cell. But at each node, there are only 3 edges meeting. And you see that there is a nice proportion between the number of edges and the number of sides and the number of edges meeting and the number of sides. Meaning if I have a cell with more sides, I'll have less room to fit them together. So that I have an inverse proportion between the two. In this case, all nodes are regular, and of course, we have plenty of examples like the honeycomb, for instance. Okay, these 2 examples. Now I want to organize my finding, and what we do as mathematicians, we put that in the plane. We call it the symbolic plane. It's also called, we call it also the Schlafly plane from Ludwig Schlafly, a 19th century mathematician who worked on polytopes. His work was completely ignored until recently. And what I have is on the x-axis, I have n, right? The degree of the node, and I have the number of corners v on the y-axis. And so I told you I can take any tilings that I have, like Alhambra or the one I show you, compute this number and put them there. And the first result is exactly the one that I told you. If I have a regular tiling, there is an inverse proportion between the 2 quantities. It makes that they are on a hyperbola. Here is the 4-4, the one that we understand, very easy. Here's the one we saw, the hexagonal lattice, and the dual of this one is the triangular lattice. It has 6 and 3, right? And all the other ones that are there, all the regular tiling are on this hyperbola. And here is a couple examples. You can create plenty. You can populate everything around. But you can also go around and look at different tiling that you observe in nature. And for instance, if you look at a fracture that you can find on rock due to motion and all that, what you see is that because of this shearing motion that you have in fracture, you have lines that creates naturally a tiling. And we call that primitive tiling, a tiling that's made of random line in the plane, like in this case. and I want to be able to say something about this primitive tiling, well, if I take random lines in the plane, the probability that the two lines will join is 1, right, at this intersection. And it's very unlikely that three lines would meet at one point. That's probability 0. So automatically, I know that n equals 4. There are 4 cells around that node. And I can use this theorem to conclude that, on average, the number of sides of primitive tiling is 4. I might have 5, 3, 4, 6, etc. But on average, it's going to be 4 for a random tiling. So that's one example that I have right away. And I can place that in the symbolic plane right there. OK, now we understand something about regular tiling. And of course, you want to know about irregular tiling. What about this irregular tiling? We know this from school, of course. So what about irregular tiling? Well, there are also plenty of examples. Here is an example which is made of 2 squares, the yellow and the red. And you see that there are 3 edges meeting at each node. All the nodes are the same. But there are only 2 corners, right, because of this T section. There is the corner from the red one below and the yellow one below, but not at the top one. So n star equals 2. And all nodes are irregular. In every single node, there is a T junction. So P equals 0 in this case. And that's how we put bricks, and that's how cell, for instance, in plant tissue also organized. There's plenty of good reason to do that, because that creates a stronger structure. So where do they sit, the completely irregular tiling? Well, more or less, they follow more or less the same kind of law, meaning that there is an inverse relationship between the degree and the number of edges, and they sit all right there. OK? So now we have started having a good understanding. What about everything between irregular and regular tiling, where all convex polygonal tiling sits in the symbolic plane in that little zone here? Right? And now we have a complete classification, and we can go around. And that was Gabor and his group did for many years. They went around, took pictures, and computed things, and computed this average, and look at the different example, and they all fit somewhere there. So they've really, everything that you find polygonal sits somewhere in this plane. And this is also the start of our conversation of what I want to tell you about today. The important message is, OK, we understand that, but is there something else? Well, we know of other type of tiling, hyperbolic tiling. We know that there are non-convex polygonal tiling here. But what we were interested in is, are the tiles with fewer corners, softer corners? Well, we know that polygonal tiling, the minimum number is 3. You can't have a polygonal tile with 2 sides, right? So if you want something there, you'll have to curve things. Is there something there, and how do we characterize them? And this is, in a way, the new thing that we've been working on, is the notion of soft tiling. It's not so new. Again, if you go back to Hokusai, 1824, you look at some of his design. And what you see here, if you look at this shape here, each shape looks like a little banana like that. And this has only 2 corners. They're all different size, but they all fit, and you have a finite number of them, and you can tile the whole plane like that. So this is what we call a soft polyhedric tiling. Next question is, can you tile the plane with a single cell, a single soft cell with 2 corners? Well, let's go back to Hook, micrographia. This is a drawing of tissue of seaweed. And if you forget about the little barbs, what you see is a cell here that repeats itself. And if you apply the same law that I give you, if you look at one node, there is, at one corner, there is only 1 corner at each node. And there are 2 corners together. So I have V star equals 2 and N star equals 1. If I make them a little bit straighter and put them together, they start looking like this shape here. Okay? Another way to think about that is I can start with a cell that I know that tiles the plane, and I can soften it by moving the top edges up and the bottom one up also at the same time so that they still fit together. Right? So I go from 4 corners and 4 edges to 2 corners and 2 edges. And then I can put them all together like that and fit the plane. Okay, here is another example. You can go to the wine store. You can buy a nice bottle, and they'll give you the wrapping. You throw away the bottle and keep the wrapping. And what you'll see is that these are also naturally soft cells. Each of these can tile the plane just by this lenticular shape. And if you look at one node, each cell has two corners, and each node has two corners meeting. So in this case, I have V star equals 2 and star equals 2. Can you do better? Well, that's the result of the next theorem that tells you that the minimum number is actually 2. You cannot have fewer than 2 corners for shapes that will tile the entire plane for a single shape. Okay, so this is a bound that we have. But now that you think about softening a given lattice, you can start with any lattice that you have, and a straight one, and say, oh, am I going to soften this? Well, it's not soft because at the edge you have corners. So the way to do it is to move a little bit the corner so that the tangent at a node becomes straight. So what you take a node, and what we're going to do is bend it, and then do the same at every node, and then look at the other type of nodes, and bend it again, and now you've removed all of them like that. And then you have a nice shape. So there is a direct way to go from a given lattice that you want and soften it to one with fewer corners. And it's not that complicated here, but we're going to apply the same process when we get to 3D. And now you can take the 3 types of regular lattice that we know in the plane, the triangular, the square, and the hexagonal one, and you can soften them into these different type of shape, and we have a complete classification of this shape. So we call a soft tiling something made of soft cell. It's a soft cell if it has the minimum number of corners. And in the plane, that's 2. A soft tiling is made of soft cells. And again, you look around, it's quite amazing because mathematicians for thousands of years have been thinking of fitting the plane with straight line and all that. But you go look around and you find plenty of shape in nature, like in rivers and all that. And when you look at shape, they're all like soft. Here below is the shape of a fungus as it grows. You have epithelial cells, the way they order themselves. Here's a piece of wheat. Blood cells naturally take this shape as they go faster and faster in the capillaries, but also in architecture. For instance, the work of Zaha Hadid is clearly not inspired by this idea, but connect directly in making this more organic shape with fewer corners and fewer straight edges that you find. You'll find them, of course, in the work of Escher, because he's been looking at all possible ways of tiling the plane, and this is one of the possible ways to do so as he explored there, completely intuitively, of course. Okay, so now we have a decent understanding of what's going on in the plane, about this soft shape. I want to go and start talking about 3D space. And of course, things are right away much, much more complicated. So for one thing about 3D space, in the plane, every regular polygon exists. You can have a 2-side, 3-side, 4-side, no, not 2-side, 3-side, 4-side, 5 sides, and n side. But we know since Plato that there are only 5 regular polyhedra, and these are the one. And Plato had this idea that they make the constituent of all the different possibility, fire, water, the universe, Earth, and so on. And the cube, for instance, is the constituent of all Earth. In a way, you can think of that. He was thinking of atoms, he was thinking of things filling things, and so on. So I think the basic idea of the tiling, that something is only made of one shape, was already there. But then came Aristotle and says, wait a second. There is something that's not right here, because these 3 shapes, they're regular and all that, but they don't fill space. You can't put them together. There are only these 2 shapes that can fill space, which is the cube and the regular tetrahedron. And okay, the cube is quite clear. If I take a cube here, this is a Rubik's cube, another Hungarian invention. So if I take a Rubik's cube, you say I have 4 cubes here, and if I put 4 more here, I would fill it, and at one node, I have the degree of one node is 8. I have 8 cubes surrounding every node, right? So you can ask the same question about regular tetrahedra. How many tetrahedra do I need to put together in space to fill it completely? And for once, I'm going to ask the audience for their opinion. A little vote here. Somebody wants to venture a number. How many tetrahedra do you put so that you fit them completely? Like we know, hexagon, you need 3. Here for cube, you need 8 cube. Anyone wants to try? I will repeat that for the audience over there. 16. Well, I have 16 here. Let's do an auction. Price is right. Come on. 12. I have 16. 18. 36. They're all good numbers. But the reality is that if you look at how many you need, it's 22.79. The regular tetrahedron does not fill space. And that was only understood later. Of course, there are plenty of other tetrahedra that fill space, like I have these magnetic toys here. It's all made of tetrahedra, as you can see. They're not regular, but you can directly demonstrate that they fill space. I put them in a cube, and then I can have as many cubes as I want. There's a big space of tetrahedra filling space, but not the regular one. However, let's go back to our friend, the octahedron. Here is the octahedron. Aristotle knew it didn't fill space, but what you can do is the following. You can truncate it. You can truncate the edge here, and to obtain the truncated octahedron, we see an example of an Archimedean polyhedron. And in that case, you can put them together. And that's a very important one. It was studied by Fedorov, the mathematician, and Kelvin, the physicist, the mathematician, at the end of the 19th century, and we'll go back a few times to that. There are other shapes, the so-called parallelohedra tilings. These are the 5 possible shapes that can fill space by pure translation. You cannot rotate them. You just pack them like cubes, if you want. Okay? These are only the 5 possible shapes that you can do. Of course, you can change the aspect ratio of some of them, but in terms of geometry, these are the only possible shape. And you see in the middle of the truncated octahedron, and the cube is part of the parallelepiped family, of course. Okay, so plenty of work, thousands of years of work on different polyhedra and tilings and all that. So what's the angle here? Well, the angle is the same as before. Is there a version of this polyhedra that's softer than the regular, the one with straight faces and edge? So remember, we started in 2D. We had 4 corners and 4 edges, and then we reduced that to 2 corners and 2 edges. So a question for you is, I take the cube. Okay, let's count it as 8 corners. 12 edge, 6 faces. Is there a way to move the edge, change the shape of the faces so that I can soften it, reduce the number of corners of that shape to make it a little bit more organic? And how far can I lower it? How far can I go? What is the soft cell in 3D? How many corners? Okay, so back to the auction. I'll take any numbers.
You can round top, so having one at the bottom 4 corners. So you can round top.
Yeah.
Round
so your number is what, 4?
So half of the corners. You have
A half. So I have, okay, very good. That's already good progress. We went from 8 to 4. Can somebody venture better than 4? Good intuition, yes. You don't have to raise your hand. It's not. Yeah. So how many corners would that give me at the end of the day? Oh, maybe none. That's interesting. Can we do that? That's maybe a little pushing it. Okay. And congratulations, price is right. The minimum number of corners is 0. There's so much space in space that you can deform things to remove all corners. And I give you a theorem, and you say, OK, I want to prove. This is not a one-line proof. This is a one-image proof, because this is the proof. This shape here that I have here, right, a 3D printed. And if you go along, you see that it has only one edge, it has no corners, and only two faces. Okay, that's the first part of the proof. There is a shape like that that exists. The second part is that it has to tile the entire space. Okay, here the second part of the proof is that I can take two of these shapes. They have the same the same shape actually, then that is symmetric. I can put them together, and when I put them together, I make a long prism. I can put as many as I want. That has a square section, and then I can pile the prism in the other direction as I want. And that's the end of the proof, right? It's quite remarkable. But of course, this is just the start of the idea. You know, this object exists, and the minimum is 0, a soft cell is 0. How do you do that in general? Okay, so again, the idea is edge bending. You look, for instance, going back to the cube lattice. If you take a cube lattice and identify one node, so you pick one node, what you must do is make these tangents disappear so that they go smoothly together, so that they align with each other. Okay, so if I just focus on that and follow the colors, what I have now, I'm going to start moving these edges and moving the one below as I must do. I do that on one node, so I have to do it everywhere else because I have a lattice. And then I extract that one cell, and now I have a soft cell here. And since I can wiggle things around without changing the number of nodes, I can transform into this shape. And then when I have this shape, I can color it and pile it on top of each other. And so this edge bending process can be done systematically to any kind of given lattice. You can soften any kind of lattice. So it's quite interesting because to see the progress of things are going in mathematics or science in general. 2 years ago, we had these ideas that you could do that for any lattice with a few very minor technical conditions. And so we put that as a conjecture. We had an exact test of how to do it, that a certain condition had to be satisfied. And then we published that. And this morning, I received an email by 2 mathematicians and says, oh, we really enjoy your paper, and we've been working on it. And we have this new paper that I'm sending to you, where we prove that your conjecture is actually right. And generalize it, of course, because they're pure mathematicians and they like to generalize things. But they actually prove it completely, that you can start with any given known lattice and systematically apply this process of bending edge to soften and remove the corners. And here is an example, or favorite example, the truncated octahedron. If I look at the wireframe, I can put it together and tie the whole space like that. Now I can take an octahedron, truncate it, apply the edge bending algorithm, and get this shape. And this shape is super nice. It has no corners. It has very nice faces that we chose to be as minimal surfaces. So if you look at the edges here, the surface that we decided to put on top of it is the one that minimized that surface, the surface area for that given boundary. And so the wireframe looked like that, and you can put it together like that. So you can now start with any shape and apply systematically this step to create a softer version of that. You can go look around in architecture, for instance, and you see some of these ideas also expressed in different shape and different instances. But a much more interesting project application is something that we started talking with people, designers at California College of the Arts, and that's the group of Margaret Ikeda, Negar Kalanta, and Van Jones. And we've been working with them for the last 2 years with different ideas, and that was one of the first ideas, to use this shape as building block. Not only as building block, but this shape actually made of eggshells. So they went around San Francisco and asked all the diners during the morning breakfast, can you give us the eggshell? They cleaned it, they ground the shell, and then they added gelatin and some bacteria to make it hold together. So these are completely bio in any way, sustainable, and they have extremely nice property as natural building block. And as a result, they have a lot of different applications, and they won a biodesign challenge based on that. A wonderful work that they've done, really beautiful. So this shape by itself, the fact that it's a different shape, gives not only ideas, but new possibilities. And in particular, they tested the strength of it, and that shows that it has better mechanical properties than a regular brick. But the application that I particularly like, and that's how we started talking with Gabor, you can find it deep in the ocean. So people who came for my third lecture in Gresham about seashell, you've learned all about Nautilus, the iconic shape that has a logarithmic spiral, and we've talked about different property of that. But today I want to talk about another property. It has the logarithmic spiral, but it has also all these chambers that you see. That's a characteristic of cephalopods. And these chambers are used by the animal to regulate buoyancy and go up and down so that they can come up from deep in the sea during the night in order to feed. There's a little opening, it's called the siphuncle, there where it can regulate different type of gas, and with that change the orientation and go up and down. Beautiful, beautiful physics. But the interesting thing is what is the shape of these. And you see that they have the lens shape, the same one that you find in occusite, but the interesting part is the shape in 3 dimensions. And here is a CT scan of that shape. So now we see the shape in 3 dimensions, what it looks like, and you can extract it. It's a beautiful shape. So it is one chamber within the Nautilus. And you can extract that one chamber, that's what it looks like. And again, you can change a little bit the shape without changing the corners or anything like that. And we change it up to a shape that looks like this one. And this one is a soft cell. So the Nautilus chambers, as it creates these chambers, for reasons that we partially understand, create naturally this soft cell. It doesn't have any of these corners that are difficult to maintain, but can also be mechanically compromising for the overall strength of the material. So it's a very natural shape, and then you can either do prism or increase the size with that same logarithmic rule and fit the whole space like that. And you can see that it's an example of a soft cell. There are other examples, but in order to do that, I have to tell you about bubbles, soap bubbles. So if you blow a soap bubble, naturally, without disturbance, it's going to take the shape of a sphere, and that's a balance between the inner pressure and the surface tension that try to minimize the surface area. And we told already about this minimization of surface area here. So a shape by itself, a soap bubble, will be naturally spherical, but when you put them together, you have the role of the pressure, but you also have the role of the contact line balancing mechanical force. And in the 19th century, Lord Kelvin, tried to understand foam, soap film, and foam in general, and tried to see if there was a simple model for it. And his first idea was to use the truncated octahedron, but he realized very quickly that it doesn't fit the basic rule of mechanical equilibrium at one node, because at one node, when you have 4 different edges meeting, you must have the same angle in all the faces. And the truncated octahedron has this 120, 120, and 90 degree below for the square. And he says, okay, I can change a little bit, just like we do. I can soften a little bit. These are not soft cell, but they're softer than one because they're not straight edge. I can soften the edge, and I can soften the faces to make what we call now Kelvin cells, which has the same angle, about 109 in each, all the way around, the 3 angles, and that satisfies the physical law and also can fit together. And up to this day, this one shape, the Kelvin cells, is the one that is conjectured to have the minimal surface area for given volume as a single shape that tile space. It's still an open conjecture, actually. That's the first interesting thing about soap film. It's almost a soft cell. It goes into softening, but it's not quite there. The other thing is that it's also directly related to minimal surfaces. If you fix the boundary, like two circles, what you obtain in a soap film is a catenoid. It's the minimal surface, it's the minimal area for the given shape, for a given surface that has the two circles as boundaries. And as you see in this picture, you can make it much more complicated. And why am I telling you that? Because Gabor went further. He says, OK, I can take the wireframe of the soft truncated octahedron, dip it in the soap, and the shape of the film on the faces will naturally take the shape of the soft cell. And so all you need to do is dip it in the soap. Well, it's very hard to do with everything, but it takes a long time. But in principle, it naturally adopts its shape just by giving the edges around. Okay, we'll get back to soap film in a second. So soon after we published the different results that I just talked about, essentially, we realized that there was an interesting connection with a completely different mathematical object that's very well known in geometry, which are called triply periodic minimal surfaces. And here is an example of them. I'm going to tell you a little bit more about that. But before I do, let's go back to our friend, the truncated and the soft truncated octahedron. And let's look at a little bit differently. So we started with the truncated octahedron, and we soften it. And so how do we do that? Well, we actually don't change the position of the node. What we do is change the tangent at every node. So the tangent here, or the half tangent, is horizontal. Every node is the same, so I can only look at one. It's a very highly symmetric object. So I have the cage there dotted, and to go from the truncated octahedron to its soft version, all I really did is change the tangent. That was the edge bending, so that now the tangent gets moved from one to the next one, right? And so that's what I can do. You can see here, I have two more space here, so the question is, what else is in that picture? Well, you can bend the edge a different way. Instead of going up, you can go down and create another soft cell, surprisingly. And this soft cell looks like this. It looks like it has a little piece of that. And what's remarkable of that is that this soft cell is the unit cell of the Schwarz primitive surface. So now I really have to tell you about this triply periodic minimal surface. So you can divide three-dimensional space with a plane so that you can have yellow on one side and blue on the other side. Or you can have a surface like this one that splits the same space in outside and inside, or blue or yellow, with this intricate minimal surface. And it's a minimal surface because it has the same characteristic as the one before. It's triply periodic because I can take one unit cell and translate it periodically in the three directions to create the whole thing. And that unit cell is a soft cell on its own. The Schwarz P surface, it's at the end of the 19th century, was the simplest one, and really these get very hard to understand. So the complement of that on the yellow side is also a Schwarz P surface. So it's called double labyrinth, and the name really evokes, because they're quite hard to picture. This is the only one you can really easily picture. So you have a double labyrinth because you have two of these structures sitting on top of each other. And if you make cement blocked, it would look like that. So you see here, the first floor is only connected to the third floor, and there is no connection in the second floor. That's why you have two labyrinths. Okay? And these shapes, remarkably, they're not just a mathematical oddity. It turns out they're fundamental in many different aspects of science. In biology, they appear because fluid membrane tends to have these minimizer properties. And so cellular shapes often take the shape of minimal surfaces. And it turns out, for instance, in the description of the coronavirus, this type of model are used to describe the different shape with negative curvature and so on. In engineering, people use these as microstructure because they have a lot of interesting property in terms of thermal property, mechanical property. They have photonic band gaps, so they have different optical properties and so on, so they're extremely used in that regard also. And now they are a typical type of design for microstructure in a lot of what we call smart material. This is just the primitive one, and I've left a space in between, so I have the hard truncated octahedron, I have the soft version, I have another soft cell on the other side, and all I did was I have a family that I obtained just by changing the tangent. And the question is what's in between, and lo and behold, what's in between is the Kelvin cell. There is a particular angle that makes the Kelvin cell. And now you see all these different structures, the hard one, the soft one, another soft one related to P surface, and the Kelvin cell related to soap bubble, all coming as part of one big family that is connected by this transformation of edge bending. Really remarkable. And that's just for the Schwarz P surface. Of course, now you can look at there are entire family of triply periodic minimal surfaces. And what the Schwarz was in 1865 or something, and described the Schwarz D surface. In 1970, Alan Schoon discovered other ones, the gyroid, which is even more complicated. And what you see is the unit cell themselves are soft cells also. And you see the gyroid or the Schwarz D surface, just trying to understand the labyrinth that goes in and out is quite difficult. And that's why also, because it's a labyrinth that connect two at the interface, you can have a lot of nice property if you have two liquid and something like that. So if you had oil in the blue side and vinegar on the yellow side, you would never be able to make vinaigrette, right? They live completely separately. But if the interface is made with the right property, you can have a lot of exchange there. And that's what engineers use for that. An example of that, this idea, a so-called Dieburg copolymer. So these are macromolecules that compose of two distinct polymer chains. So when you mix them, naturally they would separate, but they are also covalently bonded, which is quite energetically difficult to pull them apart. So they want to be apart, but they want to remain connected. And the balance of the two is to make these, again, very complicated labyrinth that's not a simple triply periodic minimal surface, but have components of different ones. And in this case, you can think of these unit cells, these soft cells, are mesoatoms for this polymer. And you can see that you can really do like Lego and bricks, put them brick together to create this more complicated shape. So they're quite remarkable on a lot of respects. And we found now entire families of them related, which are different than the typical families that have been explored in mathematics so far. So the last thing that I want to talk about, we went deep in the sea, and what better place to do space filling than to do space filling in space, of course. So when we published the first paper, it had a little bit of press and all that, and my friend Gabor managed to convince the Hungarian Space Agency to say, why don't you take one of these nice shapes to space? I say, yeah, but what are we going to do in space? But here is an interesting experiment. Why don't you just take the wireframe of the soft truncated octahedron, the one in yellow, and fill it with water? So in space, no gravitation, no gravity. So if I have water, it would naturally take a spherical shape, except that if I have constraint at the boundary, if I put like a circle, it will try to attach the circle to reduce its surface tension at the interface, right? So if I have a given shape and fill it with water, what I would have is that if I have just the right amount of water, the shape itself, the entire volume, would take the shape of a soft cell. And that's what it did. So in July 2025, last summer, they went to the space station and started to fill with water that. And you see, it's quite beautiful with all the light and things like that. And as I say, it's the first instance of a 3D shape in negative surface curvature in space, okay, realized from liquid water. I'm not exactly sure it's, it's not going to change the world, but it made this astronaut really happy. And that by itself is something. You can say, and it's so cool, right? It's shape in space. Okay, so let me conclude with a few points here. So what we've seen is that there is a systematic way to soften this shape, and you can say, what's the point? It turns out that what we systematically found since then, and that what we had before, just like with the Nautilus and other shape, is that there are many shapes in nature that naturally adopt these soft shapes, and that they are better descriptive of what we saw, that what we see, rather than the traditional flat ones. Even if you look at the honeycomb, you realize that if you zoom enough, well, the honeycomb is not perfect. This shape actually are round at the edge, and if you think of the space in between, these are actually soft cells also. It turns out that it takes an extraordinary amount of energy and organization, and typically extra protein, to create polygonal tiling within biology. And for 3D cell, we have a partial classification of some of the shape, and now I haven't read the detail of the paper, it's still not peer reviewed, but according to the mathematician, you can do it completely systematically. And there are plenty of other type of soft cell, like associated with the triply periodic minimal surface. You can have carbon allotrope that form this Schwarz side that are also part of these properties that are the same geometry. You can have various types of microstructure, but one of the nicest one is the one that you find on butterfly wing, and here is an example of a weevil. You wonder why they're so glittering. It turns out that the shape, the type of structure that you have right on the wing, or the carapace of these, are made of different layers that organize themselves very closely to triply periodic minimal surface that create optically photonic gap that create all these glittering aspects. And so there is a natural way that nature used that for optical purpose, in particular the gyroid. And probably most importantly, when we were done with that and we received a little bit of press, Scientific American called us and told us that it was the coolest mathematical discovery of 2024. We were top one on the list. So that's one for the bucket list, I guess. So again, thank you very much. And I want again to thank my collaborator, Gabor, Akosh, and Christina.
So, Alain, thank you. That was, as always, fabulous. But what beautiful images that we saw there, and how amazing to have your tilings in space. I mean, that's pretty good. Pretty good. So we have some time for questions, and I'm monitoring the online ones. But while we're waiting for that, are there some questions in the room to start us off? You can raise your hands, or you can look at there. Okay, there's one here. So a microphone will come to you so that everybody can hear the questions. Thank you.
Thank you. I was really interested in the soft cell that you displayed that was with the California College of Art, which you were using for bricks.
Yeah, so the geometry is this one. I don't have one of their bricks. I forgot to bring back. I'm just back from San Francisco, but I forgot to take one of these. And they have it they made it out of the eggshells.
That's right. And my question really is about whether those bricks and their sort of application in real life, if they could be produced, would need to be glued with cement, or they can just fit together and not have that adhesive.
Yeah, so it depends on the application. Typically, you would need some type of cement also to have that. But there are plenty of cement that you can use that can also degradable and things like that. So they've thought about that. And they've made little one and walls and stuff like that. Also, it's very appealing aesthetically. But we have collaborators in Texas, at Texas A&M, and they did the mechanical testing of this structure compared to the same type of structure, which are just cube or bricks in general, and they have better properties for building, it turns out.
Excellent. There's another question there, and then there's one at the back afterwards.
You dealt quite comprehensively with 2 and 3 dimensions. Has any work been done in 4 or higher dimensions, and if so, does it have any practical applications?
So I don't know, probably not. So polytopes and the forms like that, people have looked at that in geometry for a long time. And there's not only generalization in higher dimension, but with different type of geometry. We can do different type of geometry, hyperbolic geometry and all that in 2D or on a sphere. There's plenty you can say already there. There are results there that I didn't want to talk about, where you can actually modify this theorem by directly indicating the type of manifold on which you try to tile, whether it's a sphere, a cylinder, and things like that. So that's one thing that you can easily generalize. You can do the same type of trick. As soon as you're into 3D, it becomes very complicated to classify or understand everything. And there's plenty of work that is done in 4Ds for typical structure like hypercube, hypercube and higher order lattice. I don't know, and that doesn't mean anything, I don't know any real work on softer version in higher dimension and what are the basic results there. I think it's a little too new, and I hope that it will kind of be a good motivation for mathematicians and others to start looking in higher dimension, higher geometry. Whether or not it would have an application, higher dimension, you know, we talk about general relativity, string theory in higher dimension, straight space. Not impossible, I would say. I would say we look there. The worst things have happened in this type of theory. So yes, why not?
There was a question at the back, and then we'll have some online.
I'm not familiar with your previous work, but I'm an artist and I paint hand-painted tiles, which is a totally different thing. And I'm wondering, I'm assuming that your initial motivation for your research was just purely the enjoyment of higher math and the way that this eventually grows into an application that can be used. I'm assuming that was possibly accidental. And then I'm wondering, most of the things that you're making, do they go into building and industry, or could they be also translated into fabric and textiles?
So a bunch of nice questions. Thank you very much. My motivation typically is not pure enjoyment of the mathematics side, as much as I enjoy it, and it's perfectly valid. I wouldn't consider myself a classical geometer as part of the discipline of mathematics. So most of them, my motivation come around, and that's what I try to put in my previous talk, about going around, looking at nature and trying to understand it with the tool that we have, and if I don't, develop the tool that we need for that. And this is a good example, right? We see things and we say, is it exactly what we've been told all this year? The honeycomb is almost a hexagonal lattice. What is the difference with that? And look around all these shapes. They're not characterized by textbook things. So what are the characteristics in there? That's pulling the thread, and then you find general result, and then you find plenty of, you start looking around, find plenty of application, and you go back and forth. And there is immense enjoyment just there, as well as proving a more formal result. These shapes have not been directly used as construction material. I hope they are. I hope that architect and other designer will use them more systematically. It would be wonderful. We have plenty of other ideas with the same group that we're trying to use this shape for, again, for different applications that we are exploring. So that's one wonderful to play with these as a direct design for the real world. In terms of fabric, I don't know, but there are plenty of problem with fabric often is to find a good design that you can repeat and all that. And I think playing with these styles and patterns has always given designers a lot of good ideas. So let's hope it does again.
Well, we've just got time for a couple more questions online, so I don't want to leave out those people. And one is, you showed, you showed a diagram, a tiling from the Alhambra Palace that had some curved tiles. are they soft? Is that a soft tiling?
No, it's not a soft tiling because some of the shape have too many corners, but you can soften it because it has little star, and you can start soften. If there is a way to soften this tiling, I believe that
Okay.
you can.
Okay, and so final one, but then perhaps people in the room, Alain, might be very happy to stay afterwards, just a couple of minutes if you have questions if you're in the room. But final one for the moment online is, so could you make a tiling, I think I've understood this, could you make a tiling from, you had lines before,
Yeah.
a random tiling made from lines, from random lines. Could you do that with circles? I guess
So
worry about intersection points.
yeah, no. So that's very interesting. It's a very good question. So I've played with the following ideas. It has an application that we can talk about giant lilies, but that if you take circles and you start growing them like you grow lilies in a pond, then they will reach a certain size and then start pushing against each other. And what we've been working with Gabor recently is that if you do that, the tiling that you obtain, if you turn the void space also a tile, is a soft tiling automatically. Nature would naturally generate in the process a soft tiling in that having random growing circle expanding and touching and pushing against each other without deformation. Okay. So that would be an example. You can do the same type of, you can look where for people who know Voronoi tiling place, so that's the tiling that you obtain by taking random set of points and looking at the edges that are made with equal distance from different points in space. Or it's dual, which is the Delaunay triangulation, which are all made of triangles. These are the two random tilings, and they also fit in on that hyperbola, but they're not soft. Thank you.
So we'll finish there, but just to remind you that Alain's next, and I think, is that final lecture of this academic year next time is on
Yes, the
NOTS?
last one is going to be on NOTS.
9th of June, I believe.
I don't know.
So
Yes.
don't trust me. Go onto the website, check it out, and you can watch all of his other lectures online as well. So let's finish now and thank Alain very much for a wonderful lecture.